G'day, welcome to the second one of these videos. In this video, we're going to kind of address a question that plays on my mind a bit and is a bit of a trope in machine learning studies, which is you don't need to use machine learning for that. Um, what does that mean? So often people in this area of research will apply machine learning algorithms to certain tasks that could just as easily be achieved using traditional statistical hypothesis testing. Well, in this study, we're going to take a look at some traditional statistical hypothesis testing. We're going to kind of show how, yeah, machine learning algorithms do a much better job of certain things. And one of those things does appear to be examining sound symbolism. Of course, this study that we're dealing with, we're kind of going to be talking about automatic emotion recognition and sentiment analysis. And obviously those require a functional algorithm. So that's something that traditional statistical hypothesis can't do. It can't provide you with, like, the output can't give you the AI kind of thing in order to do that analysis. So that's like a really obvious thing that machine learning does that traditional statistical hypothesis testing doesn't do, and that's kind of give you a usable tool at the end of it. Anyway, we created the data sets. Let's take just a brief look at the Glasgow norms because that's what we'll be working from today. So if we remember, it's arousal, valence, dominance, concreteness, imaginability, familiarity, age of acquisition, size, and gender. We extracted the phonemes from the Carnegie Mellon University Pronouncing Dictionary. And we created this very, very basic code, which just counted up all those phonemes. And this will be the data that we're working off for today and for the XGBoost models that we'll create later. Loaded required libraries, dplayer stats LME4, which should all be fairly straightforward. Broom is a one you might not be familiar with. It just provides a CSV file that lets you what does it let you do? Cut and paste into Excel without losing your formatting. So let's bring in the Glasgow norm data. We're going to run this off gender, and then we will have a talk about some other metrics and what they might do. Let's have a quick talk about these because this will be the same format for the XGBoost models. We've got the gender column, and just making sure that we've got all the complete cases, although we did take considerable care when we created the data set, which we should always do. There could be some errors in there, so we're just making sure that they're not going to pop through, but we can see that we haven't lost any observations, we haven't lost any samples, so we're good. Now, these next two lines of code are kind of important. Here we are calculating the mean gender score. Remember that that's a Likert scale, where a higher number represents masculinity and a lower number represents femininity. And then we have this if-else command, which is going to say, hey, if we get a number higher than the mean gender, I want a return of 1. If we get a lower, then I want to return a 0. So in other words, 1 is masculine and 0 is feminine. We're getting those categorical dependent variables going. Okay, so there's the dependent variable as a binary gender category. Now we're going to create the data frame using just the gender category and the alphabet phonemes. And just a checksum, if it's 0, then everything's fine, and both of those are 0. We don't need to print. We'll create the model using Poisson regression. Why Poisson regression? Talk about very briefly this study that myself and some very talented researchers published in February this year. In this study, we looked at the names of Pokemon. We used Poisson regression to examine the number of times bilabial consonants and voiced plosives occurred in the names of English, Japanese, Korean, Chinese, German, and French Pokemon. I should note here that we got the inspiration for Poisson regression from this excellent statistics book. If you are interested in anything to do with statistics, this is a good book for that, so keep an eye out for it. Where are we going? Back to our studio. Okay, so we're going to create that model, and then we're going to print the summary. Now, one of the reasons I chose gender for this is because along with another very talented researcher, I've just recently submitted a paper which examines, which basically builds XGBoost models in order to examine the sound symbolism of gender in American English. And in that study, we never actually did any traditional statistical hypothesis testing. So I was kind of interested to see how the findings of a Poisson regression analysis would align with our findings. And yeah, it's pretty much the same. Here we have the high front vowel E, which is aligned with the feminine gender, and the high front vowel I, which is aligned with the feminine gender as well. So in that study, we found high front vowels were feminine, low back vowels were masculine, sonorant consonants were feminine, and plosives tended to be masculine. And if we take a look through this data set, I don't know if we found anything to do with that. I'm going to have to go and have a look. But yeah, so T is masculine. Here we have a feminine vowel. We have K, which is masculine, so another plosive being masculine. These are near significant, which is G for masculine, and the low back vowel for masculine as well. And here we have a sonorant consonant, which is significantly aligned with the feminine gender. Right. Very, very straightforward. Pretty much exactly what we found in our study. Let's not bother with printing it out, but instead what I want to do is I'm going to show you the flaw of using this for all of the psycholinguistic domains. And that's because certain psycholinguistic domains align, like there's an effect of length on them, right? So we know that for, say, size, and let me show you, before I talk about size, let me show you this nice little trick I like to use. Coding is very repetitive. However, we can cut down on the amount of repetition by making plans on how to kind of find and replace code in order to do a different thing. So here I've just selected every instance of gender gets turned into size. I've kind of pre-planned this in a way that I can do this in the future. So I will replace all, and now all I have to do is run the code and it's ready to look at the size metric. Now, this works the exact same way, except 1 is not masculine, 1 is big, and 0 is small. So let's bring this all the way down to the checksums and make sure we don't have any errors. Nope, they're clear. Create the model, run the summary. All right, so here we have a high front vowel, and this is saying that it is increased high front vowel E is positively correlated with increased size. Same with I, increased high front vowel I is positively correlated with increased size. For anyone familiar with sound symbolism, these results fly in the face of everything we understand about sound symbolism. It's like there's one study that I found where it wasn't the case, but generally the pattern is high front vowels represent small things and more open vowels represent large things. So here, if this was an actual finding, which it's not, and I'll explain why it's not in a moment, then this would be pretty groundbreaking research considering this is American English, and American English size sound symbolism has been examined in American English, and this is not the finding that they've found. So what's going on here? Well, because stochastically, larger entities are represented by larger words, what ends up happening is you have this is not a measure of the sound symbolism. What it really is it's a measure of word length, and it just so happens that high frequency vowels like E and I are gonna turn up more often in longer words, right? So here we're kind of showing that this GLM model is entirely inappropriate for this task. I suppose that you would need to go and change this into a I'm sorry, the name of it is escaping me, a multi-effects model, and you'd have to include length. But without knowing, like without having that existing knowledge that longer words represents larger entities, and that would be kind of problematic. Another one that I wanted to test, the size one, I was pretty sure. Oh, let's take a look at this analysis first. Sorry. So here we have our lots and lots of, compared to the gender model, right? We have all these statistically significant findings, but when you take a look at them, they're all aligned with increased size. None of the statistically significant findings are aligned with smaller size. And those ones that are, such as P, it's not significant. B, not significant. K, not significant. And G, which is kind of interesting, but not significant. So the only ones that seem possibly to be aligned with small size, they're not even approaching significance, right? There's nothing to tell you that there's any kind of relationship for small things. Okay, so that's because of the size sound. Sometimes I've seen it written as the longer is stronger principle, but this isn't this is the longer is larger principle, I suppose. Anyway, let's take a look at another example as to why this kind of analysis would be inappropriate for this data set. The age of acquisition, which is AOA in the data set. Sorry, size here and AOA here. So we'll go and we'll do a replace, and then I will make my hypothesis, and then we'll test it. So age of acquisition. If you are repeatedly exposed to a word, then you're going to acquire it faster. Repeated exposure requires a high frequency word, right? Now, according to Zipf's law, high frequency words are shorter than low frequency words. So there's it's all about communication of efficiency, where like short words occur more frequently in a lexicon than long words. So we're going to find the same. I'm assuming that we're going to find the same issue with the size sound symbolism, with the larger is longer principle. Here we're going to have the rarer is longer principle, I suppose you would call it, and that would affect the scores that people have given for the age of acquisition domain. Anyway, let's run these stats so that we can test our hypothesis, or my hypothesis. Sorry, I'm going to be greedy with that one. Let's do the checksum. We've got zeros, and let's create the model. Okay, wonderful. We see the exact same thing with the size model, where what we're finding is lots and lots of statistically significant phonemes, right? But all of them have a positive correlation with age of acquisition. Now, if I were to make a prediction, and I suppose that we'll be testing this with the machine learning models, about which phones would correlate with low age of acquisition, I would predict cardinal vowels, because I suppose they are the most physiologically easiest to produce. I would guess the anything bilabial, particularly M's, P's, and B's, because these are, I guess that you might call them baby sounds, right? Because babies kind of start off with their lips as their kind of main articulator, which is why we call it babbling. Yeah, cardinal vowels and anything bilabial. For on the other end of the spectrum, I would guess that maybe diphthongs might be associated with later age of acquisition. Anything to do with teeth, so F's and V's, would probably be associated with later age of acquisition, and anything more complex, so maybe affricates, might be associated with later age of acquisition. Anyway, those are predictions for the future, and if you keep watching these videos, or if you're part of this project, we get to test those. Anyway, this is the end of the second video. I didn't want to make this one too long, considering how long the last one was. Take care.